number. Here's an ester. Q factor is a lot bigger. G, an ester adsorbs more strongly on alumina than a methyl group does. No surprise, we're doing normal phase liquid chromatography. Okay? It gets a little bit, there's two sets here. Here's the alumina set, here's the silica set. You have different Q factors depending upon whether the functional group is attached to an aromatic molecule, whether it's attached or attached to an aliphatic molecule, and the same is true on the silica. Last thing is, and without derivation, mixed solvents. He comes up with an equation for solvent mixture. It depends upon the heliotropic strength of the A solvent. It depends upon the heliotropic strength of the B solvent. Depends upon the size of the B solvent. It depends upon the surface activity, and it depends upon the mole fraction. The mole fraction of the B solvent, which is considered to be the strong solvent. So if XB equals 0, EAB equals E0A. If XB equals 1, EAB equals epsilon naught B. And in between, it's a nonlinear function. Let me come back to this in a second or two. There's the function. Here's the mixed solvent strength. This is the epsilon AB, mole fraction. It's kind of weird. This is a fairly strong solvent, epsilon naught of 1. You add a teeny tiny bit, very little bit of strong solvent to a weak solvent like pentane, and epsilon AB goes screaming up. If you add a weak solvent, a weaker solvent to pentane, remember pentane is 0, it just kind of meanders on slowly. It doesn't go, it just curves over gradually. What this is saying, and this is very important, is a teeny bit of strong solvent in a really weak solvent goes a long, long way. A little methanol in pentanol, you're going to get a humongous change in retention. A little methanol in ethyl acetate, you're going to get a moderate change in retention. Very nonlinear. Fortunately, Snyder has generated lots of tables like this, and this is very important. So here's our solvent strength of a mixture. This is pentane. And you add nothing to it, that's its solvent strength, 0. Okay, we're going to stick with pentane. If we want a solvent strength of 0.05, we add 18 volume percent of carbon disulfide, or 8, or 3.5, or 4, or 2, or 1.5% by volume of either methylene chloride, or that should be chloroform, 1.5% of chloroform to the pentane, and they'll all give you the same epsilon naught. Okay? Because these are stronger solvents as we go out that way on the table. What this means is not that they will give identical chromatograms. It means that the range in retention of the solutes will be about the same. These are called equi-heliotropic mixtures, equally eluting strength. But because we've neglected all sorts of factors in deriving these equations, these different mixtures will have different selectivities. So the K prime range will be about the same, but the band spacing will be different. So there's lots and lots of opportunities for adjusting the selectivity. And there are quite big collections of this with different solvents. Here's using benzene as the weak solvent, and then different more polar solvents mixed in with benzene to get us further up in the epsilon naught scale. Okay. There's actually an experiment that shows that his equations are correct. The data, the actual figure, the symbols are measurements of relative solvent strength of epsilon naught, and the solid lines are the equation that I just showed you. And you can see there's pretty good agreement in the cases that he studied here, and I won't go through the details, but these are the solvent mixtures that he studied in A, B, C, D, and E case. There's pretty good agreement over a fairly wide range in solvents between his mixture theory and the actual solvent strength of that mixture. So once you have the factors in this equation, like that and the size of the B molecule, you're in pretty good shape for predicting at least the range in retention. You can't nail the selectivity. There are too many failures of the model to nail the selectivity down. But it's the failures of the model that enhance the selectivity of the separation. So this is a case when the model fails, it's actually good. If it obeyed the model exactly, there wouldn't be any difference between two solvent mixtures that had the same epsilon, that give the same chromatogram. Make life simpler, but it wouldn't lead to better separations. So NPLC is really quite a different world from reverse phase chromatography. When it works, it works nicely. But you have to get used to some difficulties like water, adjusting the activity properly, and using it on the right problem. And certainly, you know, sometimes you just have to use it because you don't have solubility. And that's it. Okay. Not sure what I'm going to do on Friday. I have to look at the totality of all the lectures that are left. I may not get to ion exchange because I want to get in a little more work on method development and quantitation. So I'll have to look at where we're going to get. I'll let you know as soon as I know what we'll do on Friday. I'll put it on the Google folder. There will be a quiz on Friday. A couple of people who couldn't get here, Joe, which you couldn't get here, his family was very sick. So he couldn't get here. You may want to tell him to do something. There will be a quiz. Yep. There will be an exam on Monday. Thank you.
Monday?
Isn't it